Bienvenidos todos a la clase de física con Maestro Aloe.
Eu sou Holloway! Bienvenidos, amigos! Alright, we're gonna roll in. Bienvenidos is welcome, right? Alright, welcome, friends. Cool. What's on the board right here? V equals R... What's that goofy W? Omega. Okay, so as we're looking at this, what we have found is a direct relationship between whatever this V represents, which that's a question, linear velocity. Apparently, if you have something that's moving in a circular path or an angular path, you can find the linear velocity by taking the radius times omega, which it represents what? Angular velocity. Okay, where omega is defined, and we have this in our notes from yesterday, as some change in an angle theta over some change in time t. Now, naturally, the way that physics typically goes is, here's the idea of displacement, and then we look at a change in displacement, we call it velocity. Cool, whether it's angular or linear, doesn't matter. But then we go a step further, we say, gosh, what if my velocity is changing? What do I call it when my speed is increasing or decreasing? You're accelerating. Now, we have used which letter traditionally for acceleration? A for acceleration, right? With the subscript of g for the acceleration due to gravity, the subscript of c for the centripetal acceleration, but it's just been A pretty much all the time. Moving a little bit forward, if we talked about velocity, the natural next step along this path then would be to increase our velocity at least a little bit. So here we go. Last little piece, or the next little piece for today, which winds up being the last piece of this realistically. We are going to look at angular acceleration. Now, the nice thing is that when we make the switch to angular stuff, because theta already gets used for a Greek letter, it naturally seems all right to use omega, another Greek letter. What's Greek A? Alpha. So check it out. Angular acceleration is going to be an alpha. Now, mine always look like fish, but that's an alpha. That's what mine look like. There's my lowercase alpha. Okay, when we're talking about angular acceleration, we're going to use the same definitions. We're just going to look in that angular sense. If you want to find regular acceleration, how do you do it?
Distance over time.
Distance over time gives me velocity. Velocity over time would give me the acceleration, right? So, does it seem reasonable that this might be the same calculation, just with angular stuff instead? So check it out. Angular acceleration is equal to, it's not going to be linear velocity. That wouldn't make sense to use here necessarily. What should we use? Change in velocity would be v, or delta v, if we're linear. What about if we're talking about angular stuff? So not just theta. I like where your head's at, though. Omega. Let's just take the change in angular velocity, or omega, over some change in time, just like we always do. This formula gives us our angular acceleration. Velocity over time, all the same, nothing changes. Now, remember that this idea, just this concept that we're looking at, I imagine I've stressed it before, but you might not recall. This is calculus. How fast does something change? That's the entire question of calculus. That's it. Okay, as we're looking at this, we do want to do something similar and link this idea of angular acceleration with linear because we spent so much time with it. So here we go. We're going to just link this idea, link to linear acceleration. Cool. Why we're doing this is we want to be able to move back and forth because we're going to look at different varieties of this. When we say link, just as a reminder, yesterday we got the definition of angular velocity. Here it is. And then we started with just regular velocity and saw that, hey, it really is connected to this angular version. We're going to do the same thing here with probably less annotation, but we're going to do the exact same thing. What's regular old linear velocity? What letter? You're right. I meant to say acceleration, which I think Rafa might have noticed that. Regular acceleration is A. Do you guys agree that this is something that we've seen so far this year? This is the original regular acceleration, velocity over time. Okay, from here, I want you to check your notes for me real quick. Did we have another way to write delta V? Maybe from up above in our notes, just velocity, with angular stuff involved. I'll scroll up just a hair and I'm going to ask a question. Do we have a way to write velocity with angular stuff involved somehow? It's r omega, right? I can see it right there. That is velocity, which means if I started at 0 hypothetically, my change in velocity could conceivably be just r omega. Everybody okay with that? I'm just going to substitute this in for this v. So here we go. Acceleration then looks like it could be r omega over delta t. That is just one substitution away. Now, just like we did yesterday, can I split a fraction? I think so. I'm going to work up this way just to save a little bit of space. If I split up this fraction, I could either have r times omega over t or r over t times omega. Either one works. I'm going to propose that we should use this one, r omega over t. Now, in reality, we could have, just like we did yesterday, I could have the delta w here. That would work fine, but if we're assuming we're starting at 0, that's okay. We don't need it because it's just going to be the same. Well, geez, this looks kind of familiar. Omega over time? What is that? Holy alpha. Check it out. Our acceleration in the linear sense can be found by taking r times my angular acceleration alpha, which is just a substitution right here from what we have above. Okay, we have this idea as well. As we're going through, we have a lot of the same words that represent similar ideas. It's real easy to get goofed up. We're going to take like 3 minutes. We're going to make a small table just to make sure we have a place to reference these things consistently. And we're pretty much done at that point. So I'm going to make a small table that has 4 columns and 4 rows. Cool. So looking at this, no color choice intentional. We have some quantity that we're going to be talking about. And there's 3 of them that we use like constantly. But I also want to be able to, once we have this quantity listed, they're going to be velocity, acceleration, and displacement, just so you guys are aware. I also want us to make sure that we have the linear version of this, the angular version of this, and the way that we relate these two things together, which we've done that relation part just now. We showed how angular acceleration and linear acceleration were related, just like we did with linear velocity and angular velocity yesterday. Okay, for our rows, like this is my title column, I suppose, I'm going to use a different color for each row, and I'm going to do this very intentional. The first one that I want to see is displacement. Now, when we're talking about linear displacement, there's a real common letter that we use. If I want to know that, like if I wanted to write down known to say this is how far something traveled, it's x, right? It's delta x, but it's x is what we use. So here we go. The symbol that we use for this is x. And what's the SI unit that we associate with distance? Meters. I'm going to say, I'll write the word meter. If you guys want to just use m, you can. Okay, we have a linear displacement that we just call it x. What if and really it's delta x, but we're just assuming we start from 0. What if I want to find it angularly? I don't use x for my displacement anymore. It's some amount of angle that I've changed. What do we use for angles? Theta. Cool. So I get theta. Now this one isn't a true SI unit, and it can come in 2 different flavors, but I'll tell you, 9 times out of 10, I'm going to work in radian. There's no units to worry about with radian. It makes everything nicer. Okay, and last but not least, we have a relationship between these. In our notes, we use something a little bit different. What letter do we normally use for the length of an arc? We've used S, is what we pretty constantly use. Do you agree that if you walk along a circular path, you are going some distance that we could call x, though? So S is more common. However, I want to make sure that we have it. If x is here and here's our angular, then we have the following relationship. Your displacement in meters x, if you're in radians, is exactly equal to r theta. This is what makes radians so nice. And I know that it might kind of go over your head a little bit right now. I promise this is so much easier than degrees. Take the time to do the radian stuff. I'm here if we need it. Okay. Displacement summarized. Let's go a step further. What's a rate of change of displacement called? How fast my position changes is another way to word that. So not acceleration yet. Speed's okay, but let's get a better word. Velocity. So I just want to really, ears open real quick. The rate of change of position is velocity. When I talk about that, how fast does it change? That's all we're looking at. So we also have velocity. When we're looking at velocity in the linear sense, what's a variable that we use to represent it? V, and this time I'm not going to write the words because they're going to get too long. What's the SI unit for velocity? Meters per second is the standard that we use, but miles per hour is another version. It's just not SI. How many meters over how many seconds? That's your velocity. Now, what about in angular velocity? We don't use V anymore. Omega. Okay, this one is kind of strange. When we look at omega, I want to just call it per second because there's no real unit for it. However, I understand that that gets kind of ugly. I'm going to say rads per second, where rads is my shorthand for radian. Thank you. Cool. What's the relationship between our linear velocity and our angular velocity? Weird emphasis. V equals something. Radius times omega. Now, I'm not going to write them all, but remember that these equations over here, x equals r theta and v equals r omega, they could be rearranged, right? We could solve that for omega equals v over r or whatever the case might be. Okay, I'll pick that up in a minute. Well, what do we call the rate of change of velocity? Acceleration. Indeed it is. And I'm feeling kind of blue right now. Not sadness, just the color. Acceleration. Acceleration A, typically measured in what? So velocity by second, give me the unit for that. Meters per second squared. Or if you'd rather, you could say meters per second, which I think that one actually feels more natural for me, but it's just ugly mathematically. Every second, how does my speed in meters per second change? Cool. All right, what if it's angular? We don't use A, we go Greek. Alpha. And if we're looking at this one, we did not explicitly talk about the units here, but if this is radians per second and I just add another per second to it, do you agree that that's radians per second squared? Radians per second, or per second squared. Same thing. All right, and now I imagine there's a trend starting to be seen here. X is r theta. V is r omega, which means A is r times, what's the angular version of this? Alpha. And we're done. Okay. This table, without equations and things, this would be the go-to, the thing that I would have open in my notes if I have trouble with the units and keeping stuff straight. This is the one that I would use. Okay. We have one last little comment just to make, and I'm not going to make the direct connection, but I want you to keep an open mind and ask yourself, have I seen this in pre-calc? Cool. So, last little tiny piece of the lesson today, and it's the very last part. I have like 3 lines of writing. Super short. The last little piece, while we're talking about angular velocity and acceleration and all that, one of the things that often shows up because we're, moving around in circles and getting back to our original spot is this idea that we will call frequency. Okay. For frequency, we use a lowercase f. very specific. If I write a capital F, it makes me think that we're talking about force. This is what we're going to use for our frequency. Now, you guys have obviously heard the word frequency, but I don't know where your minds go. When you hear it, what do you think of? You think of waves and sound? I think of radio stations, but same idea. They're waves that are traveling. They're just radio waves in my mind. Okay, for this, what's the difference between a low frequency noise, if you will, and a high frequency noise? Love it. The wavelength is very different. Okay, can you give me a low frequency noise? Ooh, that's low frequency. Give me a high frequency noise. Like what we're doing when we're doing that, you can feel your throat get tighter for higher frequencies. It's because you need to shape your throat and mouth so that those sound waves come closer together. Higher frequency, higher pitch. As we're looking at it, it's not always associated with noise in this case. And in fact, maybe it's not at all associated with noise currently. But we're going to say that by definition, this is just the number of complete revolutions. Now, I'm going to call it revolution here, but I'm going to put something in parentheses as well. We could call this cycles or periods all the same, which there's our trig connection.
Can I just call it period?
Sure. The complete number of cycles, periods, revolutions, whatever, in 1 second. So if you guys, most of you are in band in here, not everybody, but middle C is where? I don't know if you guys know how much theory you know. Middle C, it's 440, I believe. Do you guys know what I'm talking about or not at all? No. Okay, some of you do. Somebody's giving me a middle C trying to. I'm not good enough to be able to tell you if it is or not. Okay, I'll tell you, the frequency of middle C when you're tuning stuff, it's 440. That's the standard. 440 hertz is what we call it. That's waves per second, 440 of them. Okay, as we're looking at this, here's an easy way to calculate it. The frequency F turns out is exactly equal to your angular velocity, omega, divided by 2 pi. Okay. Ask me about this in pre-calc. Everybody in here is in pre-calc, but that's okay. Ask me about this in pre-calc, because this kind of relates to stuff that we've been seeing already. At least to some degree. We might be able to pick it out. Now, in here, there's a lot of different ways that you can talk about frequency of something. It really common in like the regular world, common with cars specifically, we call it RPM. The frequency at which your motor runs, how many times it takes to cycle, your RPM. That's what does RPM stand for? Revolutions per minute. So when you look at your car and see it's at 2 RPM, if you look closely on your dial, there will be a times 1,000. 2,000 cycles per minute is what your car is just doing there. For all 4, 8, however many cylinders you have. Okay, other places that this is really common, and we're not going to go into it, but hertz, HZ, is also a really common frequency label. It's just per second, because if this is radians per second divided by 2 pi with no units, it's just per second in the end. Cool. Hertz is really common as well. Awesome. Trig stuff here. I mean, it doesn't really feel that triggy right now, but feels okay for this section or feels awful? Cool. All right. This weekend, I want you to enjoy yourself while you work homework 8.1, which you will find on page 207. And I want you guys, I have 5 problems for you. Number 1, 3, 5, 8, and 9. Homework 8.1, page 207. Problems 1, 3, 5, 8, and 9. And for anybody traveling, or anybody who forgets their book at home but doesn't want to miss the homework because you're working diligently, I'm going to hook it up. I'm going to give you a picture of the assignment here. Last 10 seconds of the video, it'll just be there for you if you don't want to take your book home. And let's take a look-see. So we had, we'll do this first. I already forgot the numbers, but that's okay. Focus. You can focus. So I dropped this a minute ago, and it seemingly knocked itself completely out of focus. Holy cow. All right, we're going to pause this because I don't think it wants to focus. So here is where you will see problems 1 and 3 and 5. I'm going to let this sit for like 10 seconds, but thank you, Sean. Don't trust the challenge that it says it's a challenge. I don't believe it. I can't decide how the authors decided which ones were challenged. I don't believe them. All right, and then 8 and 9 you will find right here. One's find the angular acceleration, and one is find your angular displacement. Cool. All right, Raiders, if you're watching this before the game, good luck with your game. If you're watching it afterward, I hope it went okay. And I'm psyched to have a full class back next Monday. Cool. Psyched to have a full class back next Tuesday. Cool.